All right, let's get right into it. Today, we're breaking down a fascinating research paper that kind of flips one of our most basic assumptions about data on its head: sorting. The big idea here is that for years, we might have been leaving huge amounts of performance and storage savings on the table, all because we weren't thinking creatively about something as simple as order. I mean, think about it. What if we have? It's a pretty wild question. We're all taught to sort things alphabetically or numerically, right? A to Z, 1 to 100. It just feels correct. But when you're dealing with massive data sets, I'm talking millions, even billions of rows, that standard method isn't always the most efficient way to shrink its size. This paper asks, what if there's a way smarter way to arrange it all? So first, let's get the basic principle down. Sorting data before you compress it, that's a super common trick in the database world. The logic is actually really simple. If you group similar stuff together, you create patterns. And you know what loves patterns? Compression algorithms. The more predictable your data is, the smaller you can squeeze it. A big reason this works is because of a classic technique called run length encoding, or RLE. The idea is dead simple. Instead of storing A, then A, then A, then A, then A, you just store 5A. See? Sorting a column in a database creates these long, beautiful runs of the same value, which is basically the perfect food for an RLE algorithm. Longer runs mean better compression. It's that direct. Okay, so this gets us right to the heart of the problem. That standard A to Z sort, which has the fancy name Lexicographical, does a decent job. It's the default for a reason. It creates some of those runs. But the researchers behind this paper, they took a step back and asked, is decent really good enough? Could a totally different order create even longer, even more compressible runs, and just unlock a whole new level of efficiency? And this is where things get really, really cool. The solution didn't come from some obscure database theory. Nope. It came from borrowing an idea from one of the most famous, most legendary problems in all of computer science. It turns out, organizing data for compression has a secret twin. Now, here's the catch. Finding the one single perfect order for millions of rows is what's called an NP-hard problem. That's the computer science way of saying it's basically impossible. If you try to calculate the perfect solution, it would take a supercomputer longer than the age of the universe. So you can't solve it perfectly. You have to find a clever shortcut. And that clever shortcut comes from the famous traveling salesman problem, or TSP. You've probably heard of this one. A salesman has to visit a bunch of cities and wants to find the absolute shortest route that hits every single city just once before returning home. And just like our data problem, finding the perfect route for the salesman is also NP-hard. And this is the aha moment. The researchers realized that reordering rows is pretty much the same exact problem. Just think of each row of data as a city. The distance between two cities isn't miles, it's how many values change from one row to the next. So our goal is to find an order, a route, that minimizes the total amount of change, which in turn creates the longest possible runs. We're finding the shortest data path, not the shortest road path. So with this new way of looking at the problem, the paper introduces two brand new methods. You can think of them as two new sorting heroes, each designed to tackle this data version of the traveling salesman problem. They're not looking for the impossible perfect route, but a really, really good one that's also fast enough to actually use. The first one is called multiple lists. The strategy here is just so smart. Instead of comparing one row to every other row in the whole table to find its closest match, which would take forever, it takes a shortcut. It makes a few different pre-sorted copies of the data. Then, to find the next best row, it only looks at the immediate neighbors in those few lists. It's a way to find a good enough neighbor incredibly quickly. The second hero is named Vortex, and it approaches the problem from a totally different angle. If a standard sort is like a straight, predictable line through your data, Vortex is more like a spiral. It doesn't just go A to Z. It actually figures out which values are the most common in your dataset, and then groups all the rows with those values together first. This creates absolutely massive runs right from the get-go. Then it kind of spirals inward, dealing with the less common stuff later. Now, here's the secret sauce. A key feature of Vortex is that it produces what's called a gray code order. That's a special sequence where any two side-by-side rows differ in only one single column. That's it. It's an order that is fundamentally built for minimal change from one step to the next, which is exactly what we need to get those super long, super compressible runs. Okay, so theory is great. We have these two very clever new algorithms. But does any of this actually work in practice? It's time to pit them against the old champion, the standard A to Z sort, using both lab-grown synthetic data and messy real-world stuff. Right out of the gate, on synthetic data made to look like real-world patterns, the results were really promising. Both multiple lists and Vortex consistently cut down the number of runs by about 20% compared to the standard sort. That's a solid, concrete win, and it proves the whole concept is sound. But, lab data is one thing. The real world, with its unpredictable and chaotic data, is the ultimate test. So how would these new methods handle enormous, complex data sets, like, say, government census records or historical weather reports? And the answer is, honestly, it's stunning. On the U.S. Census 2000 dataset, the Vortex sort wasn't just 20% better. It made the data over 3 times more compressible using run-length encoding. Let that sink in for a second. That's not a 30% improvement, it's a 300% improvement. It's an absolute game changer. And this is straight from the authors themselves. They found they could triple the effectiveness of RLE and get these huge gains of up to 80% on other techniques too. And remember, these are improvements on top of the compression you already get from the standard way of doing things. But wait, there's a really important twist. On a different real-world dataset, this one with weather reports, the results completely flipped. Here, Vortex actually performed worse than the standard sort. The hero this time was multiple lists, which almost doubled the compression for some methods. This just brilliantly shows that there is no single magic bullet. The best sorting strategy really depends on the unique shape and structure of your data. So, after seeing all these powerful and sometimes even conflicting results, what's the actual takeaway here? What's the final lesson we can learn from all this? Well, the paper gives us some pretty clear signposts. You should think about using these smarter sorting methods when your data has certain tells, like when some values appear way more often than others. And it even gives us hints on which tool to pick for the job. As we just saw, multiple lists can be a beast for RLE compression, while Vortex is often the champion for other types, like prefix coding. But if you're going to remember just one thing from this whole explainer, let it be this simple but pretty profound idea. We spend so much time focusing on the algorithms that process our data, but this research proves that the arrangement of that data, its fundamental order, can be just as critical for performance. Which really leaves us with a final big question to think about. In a world where we are creating more data every single second, maybe the next great leap in optimization isn't going to come from faster processors or bigger hard drives. Maybe it'll come from a deeper, smarter understanding of the elegant hidden power of simply putting things in the right order.